Hi everybody, this is Quantum Mechanics with Christopher Collison, and today we're going to embark on a journey towards the rigid rotor. So this is lecture 16 of the course, and we're going to start with a very brief review, as is customary to do so in recent weeks. So we've been looking at chapter 5, which was on the harmonic oscillator. We've considered the wave functions for those vibrations. We've just finished by thinking about these Hermite polynomials, and we've described them in terms of even and odd functions. We recognize that the symmetry actually helps us with the math. We can go very qualitative in here so that we don't have to do a full solution to some of the integrals. I also introduced the idea of these recursion formulas, a particular recursion formula for Hermite polynomials, and that leads to these selection rules that are important for infrared spectroscopy. This recursion formula is also important for simplification of integrals, and we might find that again looking forward. Right at the end of the last lecture, I talked about how, in fact, we need to have an oscillating dipole moment in the molecule in order for light to interact. So remember, light comes in as an oscillating electric field. It has to have something to connect to. It has to have something to fall into resonance with, and that's this oscillating dipole moment. So we're going to find that this pops up again and again. It's going to continue as we look at rotations. So what are we going to do in today's lecture? So what I'm going to do is I'm going to present you a shift. We've got to move away from Cartesian coordinates into spherical coordinates. And homework for you will be to complete problems E5 and E7, and that ensures that you can make those jumps from the Cartesian coordinates into spherical coordinates. I'm going to start to talk about the rigid rotator. We're going to get towards rotational spectroscopy. What will happen in the first section is we'll talk very quickly about the energy levels, and I'm even giving you in this preview the equation for the energy levels. This is what's going to come out of a solution to the Schodinger equation. We've got E equals h bar multiplied by j, that's going to be our rotational quantum number, multiplied by a j plus 1 in brackets, divided by 2 times the inertia. So we might see some similarities there with what we saw previously, but we're now thinking about angular momentum. We're going to think about angular momentum and angular kinetic energy. So I'm going to set up the problem of the rigid rotor classically, and we're also going to touch today on the conversion of the Hamiltonian operator from Cartesian coordinates to these spherical coordinates. And it turns out that that is a tedious thing to do. So we won't do it in class. We're just going to use the result, and you'll see why when I get there. So what I'm going to do, first of all, let's jump straight into thinking about these spherical coordinates. So here we have our title, spherical coordinates, in here, and we've got our 3 Cartesian coordinates, x, y, and z. We'll notice that the x is kind of coming out of the plane of the paper, if you will, and we've got our y and z in the plane of the paper, and we've also got our body. And this single body is described as rotating around an axis, and the position of that body is equal to r theta phi. Okay, so we have these coordinates r, theta, and phi, and you can see our phi is this angle, and it's an angle inside the xy plane, and that angle, by the way, can go so if we think about it, phi can take values from 0 all the way to 2 pi, so we can go all the way around within that plane. we also have an angle theta in here, and that angle theta can go from 0 all the way to pi. So the question we're going to address in this piece is, so let's think about our conversion. We're used to working in x, y, and z, but what are x, y, and z in terms of these coordinates r, theta, and phi? Okay, and as I mentioned earlier, the convention is that phi here is measured from the x-axis. Okay, so what we first need to recognize is that we have this projection. So we're actually going to project this position down in here to the xy plane. And so what I'm going to draw in here now in green is this line here, and we can think about that as being equal to r sine theta. So we think of r is the length of that, it's the distance, so it's effectively the hypotenuse here. And so we've got, when we think about this, we've got this right angle in here, so this is a right angle triangle, and so we know that it's the same distance, by the way, as this distance up above in parallel. So we know from our trigonometry that that distance is going to be the opposite to theta, so it's r sine theta, and it's the same as that projection that I've shown at the bottom in the xy plane. So that's the first thing that we're going to think about. So if we want to start to consider what x is, again, so we're also going to think about this now as a right-angled triangle in here, but now the hypotenuse is r sine theta, and so the value of x, of course, which is this distance in here, that's the line that's adjacent to the phi value. So we're going to have x being equal to r sine theta multiplied by cosine phi. So that makes sense. We can also recognize what the value of y is in here. So again, taking that same right angle triangle and recognizing that r sine theta is that projection that I've shown, that dotted green line. So we now have r sine theta, and so this is going to be the angle that's opposite the phi angle in here. It's the line that's opposite the phi, so that would be sine phi in here. So now we've measured our x and our y values in here. The z value is relatively straightforward, so now we're thinking about this particular length up here. So in this particular case, we have to again think about the right angled triangle that is bound by the angle theta, and so z ends up simply being equal to r, and it's the line that's adjacent to theta, so that would be r cosine theta. So what we've done in here is we've determined what x, y, and z are in terms of these spherical coordinates. What else can we say? We can also recognize that in this particular case, r is a constant. So let's say r is equals c, which is a constant. And that means that really we have a sphere of radius c, or r, centered at the origin. We're also going to say that r is a positive number. So r is positive. Other things that we can talk about, we can also state that r is equal to x squared plus y squared plus z squared, and we'll have the square root of that. What other things can we recognize in here? A couple of trigonometric equivalencies. We can say cosine theta, by the way, is equal to z divided by, so this kind of comes from here, all right, z divided by x squared plus y squared plus z squared, all raised to the half. Another key point in here is that tan of phi is equal to y over x. So lastly, I'm also going to state to you that any point on the surface of the sphere can be specified by theta and phi. Okay, so next up what we're going to do is we're going to think about our volume elements. So we're very used to working with volume elements, right? A volume that's dx, dy, dz, and we've often said that that's equal to d tau. So what does a volume element look like in terms of spherical coordinates? So let's take a look at that. So what does a volume element look like in spherical coordinates? Well, we did have dx, dy, dz, but now we've got a slightly different system. And so what I've done here is I've shown sort of the top part of the sphere, and there's some very small channels in here. And what we can say, by the way, is this small channel at the top, we might say that this ends up being a change, as we go in here. This is a change in d phi, right? So that's the angle that goes around the equator of the sphere. And we also have this angle that goes down in this direction, which we're going to say is d theta. Okay. And so when we go back to the previous diagram, we actually recognize that these, well, we've also got the distance away from the center of that sphere. That one's easy. That's simply our dr value in here. But when we go back and think about these other things, we've got an r sine theta d phi term. We've got an r d theta term. So think that through. And of course we remember the circumference is 2 pi r, and we also remember, of course, that r sine theta is a projection of r onto the xy plane, and that d phi is that small change in the equatorial angle. That's what I'm showing here. So when you put these all together, we're going to get these three sort of coordinates in here, or these three dimensions that we care about. So let's write those down. So dv really is equal to r sine theta d phi, now multiplied by r d theta, now multiplied by dr. Let's collect those terms together, and we're going to end up with r squared sine theta, and that's dr d theta d phi. So we can actually use this and demonstrate that this works. You're probably familiar that if we wanted to evaluate the volume of a sphere, we all know what a volume of a sphere is. It should be 4/3 pi r cubed. So evaluate the volume of a sphere. Let's call the sphere, let's say the sphere has a radius of a. What are our limits? Okay, so the limits, let's write up here in blue, limits, right? So we've got 0 is less than or equal to r, which is less than or equal to a. We've got our values for theta in here, so 0 is less than or equal to theta. Remember, theta is our angle that goes down from north to south pole, so that only goes down to pi. And then we have 0 is less than or equal to phi, so this is our equatorial angle, which is less than or equal to 2 pi. So we can set up our volume in here, and we can take into account these limits. So we get a and 0, and we can split these differentials up. So r squared dr, and then we're going to go from pi to 0. That's when we're taking into account sine theta, or the theta part, d theta, and then the limits for phi are 2 pi to 0 d phi. And again, what we end up with here, of course, is we plug these, they will do this integration, so we got r cubed over 3, and that's ranging from a to 0, and then we've got our this will be minus cosine theta, and that runs from pi to 0, and then we've got our phi term in here, and that runs from 2 pi to 0. So what we end up with here will be a cubed over 3 multiplied by, well, cosine of pi is let's see, is minus 1, so that's going to be that's going to go plus 1 minus cosine of 0 is plus 1, so plus 1 minus 1, and that ends up being sorry, that's minus 1 minus 1 in here, and then we end up with the last piece is we go from 2 pi minus 0, and that comes out to be 4 a cubed over 3. Sorry, that comes out to be 4 pi a over 3. So 4/3 pi r cubed. So that's basically demonstrating that how we use these spherical coordinates to actually determine the volume of a sphere. So I'm actually going to point out to you that as I mentioned in the preamble here, so problems E5 and E7 in the homework are really important for you to do. So I'm going to say in general, we have an integral, I'm going to call this integral I. So we can take any value, of course, for the position, so for the length or the radius. We've got our pi over naught term here. We've got our 2 pi over naught term here. We've got our function. Let's call that function. Well, there's a function of r, theta, and phi. And then we're going to have the r squared sine theta dr d theta d phi. And actually we write this in a certain way. We're gonna tend to see that the integral here that we care about, we'll write this in a different way. We're actually going to collect all our terms. We're going to put the dr r squared in here, and we're going to have the pi and 0, so that's going to be followed by the d theta. So this is the convention of how we're going to write this. And then lastly, 2 pi to 0 is going to be d phi, and then we're going to put the function that follows it, a function of r, theta, and phi. Okay, so we're going to act first with this integral. So this is similar to what we saw with operators. What we're then going to do is multiply. So multiply the result by sine theta, and then act on that with that integral here d with respect to d theta. And then the third thing we're going to do is multiply the result of this by the r squared term in here and integrate that with respect to r squared. So we're going to do these in sequence, and we're going to see how this works out. So we're going to look at some functions later in the chapter, and that's the order in which we're going to integrate these functions. So let's take a break there, and we'll see you in the next video. To be continued. Thank you.